So we're looking at rational functions and how to graph rational functions. And so here is what I'm hoping that you'll get out of this video. I hope you'll be able to find a vertical asymptote of a rational function, that you'll be able to find a horizontal asymptote if it exists, or a oblique asymptote, which is also called a slant asymptote of a rational function if it exists. Be able to graph your rational function, and then be able to solve problems involving rational functions. So let's look at the definition of a rational function. So a rational function is a function that can be written in the form of a quotient of two polynomial functions. In this case, I called them P of x and Q of x. We have to say that Q of x, our denominator, can equal 0, because when our denominator is equal to 0, that's where it is undefined. The function is undefined. So last week we looked at polynomial functions, and you can see this funky notation up here, this a sub p x to the p power plus a sub p minus 1 x raised to the p minus 1 power plus dot 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 plus a sub 1 times x plus a sub 0. So that is the polynomial function. Recall, in order to be a polynomial, that our exponents had to be integers, and they had to be greater than or equal to 0, or exponents. And so we have the same thing in our denominator, but possibly a different polynomial function. Things to remember from last week that we're going to be using for this week is knowing the degree of a polynomial. So recall that the degree of the polynomial was the largest exponent of the polynomial function. Looking at the leading term, the leading term was the coefficient, the number in front of the variable, and the variable raised to the highest power. So those are things that we're going to look at while we're finding asymptotes later on and talking about graphing the function. So let's first look at what it means to be a vertical asymptote. So a vertical asymptote, what's happening is as x gets closer and closer to one value, let's say a, so let me write it here, as x approaches some value, x equal a, then what's happening to our graph is either shooting up to positive infinity or shooting down to negative infinity. So as x approaches some value a, then excuse me, then y approaches positive infinity or negative infinity. So just so that you kind of get used to the notations, and you're going to be seeing this soon, hopefully, when you get into calculus. When you're looking at this notation-wise, you'll see the limit. Oops, that's too thick. Notation, we'll see the limit. And limit is denoted by LIM. Underneath, you're looking at the variable, in this case, x, is approaching some number. I'm going to say a of our function f of x. This is going to plus or minus infinity. So let's look at what that's saying graphically. So let's say we have some value here, x equals a. Usually when we're graphing, we'll denote a vertical asymptote or any asymptote with a dotted line. You usually won't see those on the graph if you graphed it on a technology, but we put it there so we know that it's there. So as we get closer and closer to this X value, A, our graph is either going to shoot up to positive infinity. So it's going to shoot upwards. Here's an example. Or another example is maybe we're coming in on the right-hand side of X equals A, and it might be shooting down to negative infinity. It's possible that they're both going upwards as we get in closer and closer to A on the left and the right, or it's possible that they're both going down to negative infinity as we're getting closer and closer to A on the left and the right. But here's an example of what could be happening at a vertical asymptote. So the following states the vertical asymptote of a rational function may be found by examining the factors of the denominator that are not in common to the factors of the numerator. Vertical asymptotes occur at the zeros of such a factor. Okay. So vertical asymptotes, what this is saying in words, is that vertical asymptotes are going to occur on values which set our denominator equal to 0, but not also our numerator. So there are steps on finding vertical asymptotes of a rational function. So here are the following steps that I usually take when I'm looking for a vertical asymptote of a rational function. I usually start by factoring both my numerator and my denominator. I note any restriction in my domain. So remember, domain are all the values of our input that we can plug in to our function and get back a real number or something that is defined. So we have to look at restrictions, values which set our denominator equal to 0. We have to restrict those from our domain. We can't have those. So we'll factor both our numerator and denominator. We'll note any restrictions that we have for our domain. We'll cancel any common factors in both the numerator and denominator. And if there's any values that cause the denominator to be 0, after we simplified the version above, then there is a vertical asymptote, and they occur at the values which set the denominator equal 0. So part 5, note any restrictions in the domain where the asymptote does not occur. So these are removable discontinuities. So the next thing in here says to try it. And I've had the students do this before, where they go back in and they look at what was just stated and try to look at the directions and explain it in their own words with what is being said and what to do. I just think that it's important that you know the terminology. If you're not understanding the terminology that's being said in here, then you're going to be struggling with what we're doing. And so you should be able to go through and understand, what does the numerator mean? What is the denominator? What does it mean to be restricting things from our domain? What does it mean to be a factor? So you should be able to understand all those things. What does it mean when the denominator is 0, or to be a 0 of the denominator? If you're not familiar with the 0 terminology, we're going to be using that a lot in this section when we're finding zeros of polynomials. So let me just pause for a moment and let you guys reflect on what's being said here, and then I'm going to let you ask any questions. Okay, so now we're looking at an example where we're going to identify the vertical asymptote. We're given a rational function. The rational function is f of x is equal to, our numerator is 2x squared minus 18, and that is all over the denominator, which is x squared plus x minus 2. So first thing we want to do is let's factor both the numerator and our denominator. So looking at this, I noticed that my numerator, I have a coefficient that is in common with both terms, so I'm going to factor that out. So I notice 2x squared and negative 18 both have a 2 in common, so let's pull the 2 out of both of those terms. Factoring out a 2 out of 2x squared, I'm left with an x squared. And factoring out a 2 from negative 18, I'm left with 9, all over. So looking at my denominator, I notice it's quadratic, x squared plus x minus 2. I don't have any common factor to factor out of all three of those terms. I notice my coefficient in front of my x squared is 1, which makes my life easier if it's factorable. So I'm looking at my coefficient or constant of negative 2. I'm thinking to myself, what multiplies to negative 2 and would add to my middle coefficient of 1? Well, what multiplies to negative 2 and adds to positive 1 would be positive 2 and negative 1. I noticed that I can factor a little bit further in my numerator. I noticed that the factor left after I pulled out the 2, x squared minus 9, is a difference of squares. And so that we can factor that as x minus 3, x plus 3. All over our denominator, x plus 2, x minus 1. So looking at this, I need to look at values which x cannot be. So for our domain, you want to exclude values which set our denominator equal 0, because those are values which are going to make our function undefined. And so x plus 2 cannot be 0. If we solved for x there, x cannot be negative 2. And x minus 1 cannot equal 0, and so x could not equal 1. So our domain are going to be all real numbers, but x equals negative 2 and x equals 1. Notice there's no common factors in both the numerator and denominator, so there's nothing I can simplify there. And so my vertical asymptotes, we said, were values which set our denominator equals 0, but not also our numerator. So looking at this, we have a vertical asymptote. We actually have two. We have one at x equals negative 2, and we have one at x equals 1. Those are the values which set our denominator equals 0, but not also our numerator. When I'm asking you that question on an exam, don't just tell me negative 2 or 1, because these are actually equations. They're vertical lines. And so you want to put in there x equals negative 2 and x equals 1. So sometimes we might get what are called removable discontinuities. So following states, occasionally a graph will contain a hole, a single point where the graph is not defined, indicated by an open circle, and we call such a hole a removable discontinuity. So how do we find these removable discontinuities? Well, these removable discontinuities actually occur when the values which both set our numerator and denominator equal to 0. Let me just read through what I just stated in words. See if I use my highlighter. So the following states, a removable discontinuity occurs in a graph of a rational function, let's say at x equals a, if a is a 0 of the factor in the denominator that is common with a factor in the numerator, we factor the numerator and denominator and check for common factors. If we find any, we set the common factor equal to 0 and solve. This is the location of a removable discontinuity. This is only true, though, if the multiplicity of the factor is greater than or equal to that in the denominator. So if the multiplicity of the factor is greater in the denominator, there will still be an asymptote at that value. Okay, so if we have this common factor both in the numerator and denominator, it's possible that that's a removable discontinuity. That's a hole on the graph. If the factors are more, the multiplicity is higher for the factor in the denominator than the numerator, then we still have an asymptote. So looking at the following example, it says find the vertical asymptote and removable discontinuities of the graphs of f of x equals x squared minus 1 all over x squared minus 2x minus 3. So just like we had done before, we want to start by factoring both the numerator and the denominator. So looking at our numerator, we have a binomial, x squared minus 1. So that's a polynomial with 2 terms. Notice that it's a difference of 2 squares, so that's factorable. And we can factor that as x minus 1 all times x plus 1. All divided by, so looking at the denominator, we have a quadratic, x squared minus 2x minus 3, a trinomial, which has 3 terms. Coefficient in front of our x squared is 1, and so that makes it easier if it's factorable to see. So you're looking for 2 numbers that multiply to -3 and add to -2. And -3 plus 1 multiply to -3, but if we sum them, they add to -2. And so it factors as x minus 3, x plus 1. So we need to be careful here for our domain. You want to look at the domain before you cancel like factors. So our domain here, we would need to exclude the values which set our denominator equals 0, and that would be when x is 3 and when x is equal to -1. Just to kind of reiterate what we've been doing in the past and what was on your exam, you wrote this in interval notation. Our domain in this case would have been -infinity, comma, to 3, with a parentheses, not including 3, union. Then we're looking at everything from 3 to -1, but not including 3 and -1, so we would use our parentheses. And then we're looking at everything which is greater than -1, so we will write that as -1 to infinity. And those both have parentheses around them. I notice that we have a common factor of x plus 1. And so the only factor that is remaining in my denominator is x minus 3. So our vertical asymptote is going to occur at the value which sets our denominator equal to 0, the remaining factor. So we have a vertical asymptote at x equals 3. So since -1 is the value what sets both the numerator and denominator equal to 0, we have a removable discontinuity. And x equals 1. So if I wanted to figure out what is that hole, if I was going to have that point there, that's a removable discontinuity, the open circle for that point, that because it's not defined there, where would it be when x is 1? And so if you wanted to find that, you're going to look at plugging in 1 into the reduced form of f of x. So if I look at f of 1, and I plug this back into my reduced form of the equation, I would have, I'm sorry, it was -1, that it was removable. X equals -1 was what set the denominator equal 0. So plugging in -1, wherever I see an x in the factored form, so I'd have -1 minus 1 all over -1 minus 3. So let's simplify that. So -1 minus 1 gives me -2, and -1 minus 3 gives me -4. And that reduces to 1/2. So on the graph, we have a hole at the point -1, 1/2. So looking at another example, we have g of x is equal to x squared minus 25, which is in our numerator. And then in our denominator, we have the polynomial x cubed minus 6x squared plus 5x. We're looking for our vertical asymptotes and any removable discontinuities. So again, let's start by factoring both the numerator and denominator. And so looking at this, we have a difference of squares. So x squared minus 25 factors as x minus 5 times x plus 5 all over. So looking at our numerator, notice we have a common factor of x there. And so let's pull out an x from all three of those terms. So factoring out an x from an x cubed, you're left with an x squared, minus factoring out a x from 6x squared, we're left with 6x, plus, and factoring out an x from the 5x, you're left with 5. Let's go a little further. So our numerator is still x minus 5, x plus 5, all over x times, so factoring x squared minus 6x plus 5. So two numbers that multiply to give us positive 5 and adds to give us a -6. So that would be positive 5 and positive, oh no, that would be -5 and -1. So x minus 5, x minus 1. So for our domain, we need to say that x cannot be, well, x can't be 0, so that's when x is 0. X minus 5 can't be 0, that's when x is 5. And x minus 1 cannot be 0, and so that's when x is 1. So domain's going to be all real numbers except for those three just stated. Looking at common factors, I notice we have a common factor of x minus 5, both in the numerator and denominator, so those cancel. And so what's left in our denominator, the values which set the denominator equal to 0 are going to be where our vertical asymptotes are. So we have vertical asymptotes, I'm going to call it VA, at x equals 0. And we have a vertical asymptote at x equals 1. So we did have a common factor which set both the numerator and denominator equal 0. And there was no remaining factors after we canceled those, and that's where our removable discontinuity is going to be. So our removable discontinuity occurs when x is 5. Figure out where the open circle is, what that point is for that removable discontinuity. We're going to go back in and we'll plug in 5 into our function g of x. And let's plug that in wherever we saw an x remaining in our function. So we have an x remaining here. So we have 5 plus 5 in our numerator, all over, I see an x here. So I'm going to replace it with 5. And then we have parentheses 5 minus 1. So our numerator, we have 10 all over 5 times 5 minus 1 is 4. So 10 over 20, which reduces to 1/2. So our removable discontinuity is when x equals 5, and that point is 5 1/2. Okay, so we'll see, looking at finding more vertical asymptotes and removable discontinuities when we put this all together to graph. But now let's look at another type of asymptote, which are horizontal asymptotes. So what is a horizontal asymptote? A horizontal asymptote occurs if we're looking at x going to positive infinity and or negative infinity. And as x is going to positive and negative infinity, what's happening is our y value is going towards 1 y value. So let me just write this in words. So definition, a horizontal asymptote occurs if x approaches positive or negative infinity, and the graph goes to some value. Let's say y equals b. So just so that you're a little bit familiar with the notation and see it again once you get into calculus, you're looking at the limit. So saying as this x value is going somewhere, and then underneath we tell it where that x value is going. So as x with an arrow is going to positive infinity of our function f of x, this is equal to some y value of b. Or if I was looking at the x value going to negative infinity, I would say the limit, I denote it by LIM, underneath x with an arrow, negative infinity of our function. Let's just call our function f of x. If there was a horizontal asymptote, this was equal b. Okay, so let's look at what that's saying if we were looking at a graph. So again, we denote asymptotes when we're graphing by a dotted line. It's not there, but we like to put it there just to show that there's an asymptote there. So let's say we have some horizontal line, y equals b, and I'm just putting it above the x-axis, but it could fall below the x-axis. It could even actually be the x-axis. So I have some horizontal asymptote here at B. And as I'm looking at my graph, as my graph is going towards x goes to infinity, my graph is going to start hugging this line y equals b. I can hug it above or below the line. So I might have something, let's say over here, where as x was going to negative infinity, I was getting closer and closer to y equals b. So if you look at this graph, I have a horizontal asymptote at B, but I also, when I drew this, notice that it looks like my graph is getting closer and closer as it gets closer and closer to x equals 0, my y-axis, my graph is shooting down or up to positive infinity. So we actually, in this case, have a vertical asymptote at x equals 0. So that's what it would look like if we had some horizontal asymptote. So if it's not a horizontal asymptote that exists as we go off to positive and negative infinity, then it's going to have what is called either a slant or an oblique asymptote. Your book states that they call it an oblique asymptote, and they only say that an oblique asymptote occurs if the degree of the numerator is just one larger. I disagree with what the book says. I think that basically you're going to have a oblique asymptote, also known as a slant asymptote, if your graph is going to positive or negative infinity. So for instance, maybe we have the line y equal x is a slant asymptote. And so what could be happening here as we're going off to positive infinity, we're just going to get closer and closer and hug this line y equals x. So this would be an example of an oblique asymptote. The way that we find the oblique asymptotes and our horizontal asymptotes are the same way. We're looking at the degrees of both the numerator and denominator and comparing those to determine if we have a horizontal asymptote or if we have an oblique asymptote. So the next piece states how to find your horizontal or oblique asymptotes. This probably should be an and. So let me just read through what is stated below. So when you're looking for a horizontal and oblique asymptotes, you want to look at the degree of the numerator and the denominator. These degrees determine what is happening to the graph as x goes to positive and negative infinity. We're going to compare the degree of the denominator and the numerator. If the following occurs, then this is what's happening to the graph of the rational function. Okay, so there's 3 different case scenarios depending on our degree of the numerator denominator. One case is where your degree of the denominator is bigger than the degree of the numerator. So if the degree of the polynomial in the denominator is bigger than the degree of the polynomial in our numerator, then we have a horizontal asymptote that occurs, and it is y equals 0, which is also the x-axis. So this is a really important concept that we'll use a lot in calculus. So let me just kind of talk about this really quickly. So let's say we had some function f of x here is equal to 1 over x, or even x raised to any power, let's say n. As our function goes to infinity, so as we're putting in infinity into our denominator, it's growing. This value here is going to 0, which if you think about it, and let's just think of 1 over x for a second. And let's think about x. So if you plug in a value of, let's say, 10 for x, 1 over 10 is 1/10, which is 0.01. Okay, that's close to 0. If I even get bigger value of x, it's going to infinity. So if I put in 100 and I put 1 over 100, you get 0.01. Okay, that number is even getting closer to 0 than the one above. If I put in 1,000 for x, so 1 over 1,000, that is 1,000ths, 0.001, and that's even a number closer to 0. And so notice as this value of x goes to infinity, my output, 1 over x, is going to 0. So if I put in 10,000, then I get 1 over 10,000, which is 10,000ths. And so if I have an exponent here of n that is a positive integer, that is just going to grow faster than what I had just done. Or it's just going to head to 0 faster than what I had just done. So if the degree of the denominator is larger than the numerator, they have a horizontal asymptote at y equals 0. Our next case is if our degree of the denominator and the degree of the numerator are the same. If they are the same, then there is a horizontal asymptote. These are the same. We have a horizontal asymptote. And what we're looking at to find that horizontal asymptote is that leading coefficient of our numerator, all divided by that leading coefficient of our denominator. So for instance, if we had, let's say, f of x is equal to 5x squared minus 6x plus 2 all over 25x squared minus 9. I would just look at this and I would compare the degree of my numerator denominator. I would notice that my degree of my numerator was 2. And the degree of my denominator also equals 2. So looking at the leading coefficient of my numerator is 5, and the leading coefficient of my denominator is 25. So this is saying that my horizontal asymptote is at y equals 5 divided by 25, which reduces to 1/5. So we have a horizontal asymptote in this example where we have the degrees the same is y equals 1/5. And then we have our third case scenario. So our third case scenario is when our degree of the denominator is smaller than the degree of our numerator. And if this is the case, we get an oblique or slant asymptote. So your book says that this oblique asymptote only occurs if the degree of the numerator is just 1 larger. I disagree with that, and I say that there is an oblique asymptote if our degree of the denominator or numerator is larger. So just be aware of that when you're looking at the homework. And so we have two different cases. If the degree of the numerator was just one larger, your degree or your slant asymptote or oblique asymptote is going to be a linear equation, y equals mx plus b. If it was not, then really what you're going to see what's happening to your graph as x goes to infinity or negative infinity. It's going to tend towards your leading coefficient of the numerator all over the leading coefficient of the denominator. Here should be y equals. So for instance, let's say we have y is equal to 2x squared minus 6x plus 1. And this was all divided by x minus 1. So I notice here that the degree of my numerator is larger than the degree of my denominator. And so I could figure out what my oblique asymptote is by looking at long division, which is something that you're going to be needing to know how to do when we're looking at zeros of polynomials in a little bit. And so long division is very similar to long division with just numbers in it. So I'm taking my x minus 1 and I'm dividing it into my numerator, which is 2x squared minus 6x plus 1. So what we're looking at is the first term in our divisor, which is x, and we're thinking to ourselves, what do I multiply x by to get back this first term in my dividend, which is this 2x squared? Well, x times what is 2x squared? Well, I know x times 2x gives me 2x squared. So we figure out that number, that's where we multiplied it to what is called our divisor. So 2x times x minus 1, and we put it underneath this dividend. So 2x times x is 2x squared. 2x times negative 1 gives me minus 2x. So here I'm going to subtract this off. And so we have 2x squared. This is really minus 2x squared. Cancels, we give a 0. And then if I distribute my negative here, I really have negative 6x plus 2x, which gives me negative 4x. Now I'm looking again to figure out what I need to multiply x by to get this first term down here, negative 4x. So x times what is negative 4x? Well, x times negative 4 gives me negative 4x. And so we distribute this. So x times 4. So I get negative 4 times x, which is negative 4x. And then I have negative 4 times negative 1, so that's plus 4. I'm going to bring down my next term down here, which was a plus 1. So we subtract this off. So a negative 4x, this is really going to be a plus a 4x. That cancels, that gives me 0. I did something wrong if it didn't, because that's what I was trying to get before. And I have 1 times, or negative 1 times 4, which is negative 4. Adding that to the 1 above, 1 minus 4 gives me negative 3. So I'm done. I have a remainder of negative 3 because this is a smaller degree than up here. And so my quotient, y equals 2x minus 4 is the oblique asymptote. If the degree of the numerator had been larger than just one more, we'll be looking at one more example. Move it over here. Maybe we have some function f of x is equal to 10x to the 5th minus 6x squared plus 2x, all divided by 2 minus 5x cubed. So again, to see if there's a horizontal or vertical asymptote, or sorry, horizontal or oblique asymptote, I would look at the degree of the numerator denominator. So my degree of my numerator, highest power, is 5. The degree of my denominator, the highest power there, is 3. And so I'm going to look at the leading coefficient of the top, leading term, and my leading term of my bottom. And so we're going to have a oblique asymptote. At y equals 10x to the 5th all over negative 5x cubed. Well, we can reduce this. Negative 5 goes into 10, negative 2 times. And then let's use our rules of exponents. So recall, if you had some same base, let's say b to the m divided by b to the nth power. You have the same base and there's division. You're taking the exponent in the numerator minus the exponent in the denominator and keeping the base the same. So in this case, we're going to have x raised to the 5 minus 3 power. Or this is y is equal to negative 2x squared. So our oblique asymptote for f of x, as our graph goes to positive and negative infinity, the graph is going to be getting closer and closer to the graph of y equals negative 2x squared. So just a couple additional things that you should know when you're graphing these rational functions. So we just talked about how we're going to find our vertical asymptote, how to find a horizontal asymptote if it exists, or oblique asymptote. One of those is going to exist. But while we're graphing these, you should note that a graph of a rational function will never cross a vertical asymptote. We'll call vertical asymptotes occur values which are not in our domain. And so we can never have that output of the vertical asymptote for our rational function. It is possible, though, that the graph will cross a horizontal or a slant asymptote. Another word for slant was oblique. I kind of use those interchangeably. Your book uses oblique asymptote, though. And then the other thing you should know is, well, a graph of a rational function may have many vertical asymptotes. The graph will have either one horizontal or one oblique asymptote. It's not going to have both. It's just going to have one or the other. And then it's going to be helpful when we're graphing these rational functions to be able to find the intercepts of our rational function. So a rational function will have a y-intercept when the input is 0. So if we put in our input of 0, when x is 0, that gives us our y-intercept. But we have to have the condition that the input of our 0, x equals 0, has to be defined. It couldn't be that number that is a vertical asymptote or a removable discontinuity. So again, a rational function will not have a y-intercept if the function is not defined at 0. So likewise, a rational function will have x-intercepts, 1, multiple ones, none, at the inputs that cause the output to be 0. So recall, x-intercepts occurred when we let y equal 0 when we solved. So since a fraction is only equal to 0 when the numerator is 0, x-intercepts can only occur when the numerator of the rational function is equal to 0. So now let's look at putting all of what we just kind of talked about together to graph these rational functions. So in front of us are steps on how to graph a rational function. Some of these don't have to be done in the order that it's stated, but you're going to want to be doing the following to graph your function. So you should find your x and your y intercepts. So to recall, to find your y-intercept, you're going to let x equal 0 and solve for y. If you're looking for your x-intercepts, they exist, you're going to let your function f of x or y, whatever your function's called, let y equal 0 and solve for x. As I just stated before, technically all we have to look for is when your numerator is equal to 0. We looked at solving rational equations before, and we cleared our fractions when we had a rational equation by multiplying both sides of our equation by our least common denominator. So if we multiply 0 by our denominator, that's going to go to 0, and we'll just be left with our numerator equal to 0. So when we're looking for the x-intercepts, really, all we really need to look at is when is our numerator equal to 0. We talked about multiplicity of a polynomial, the zeros of a polynomial, and that told us what was happening at the x-intercept. Was our graph going to cross the x-intercept, or was it going to just touch it and turn back around at that x-intercept, which is also called a 0? So recall, if you had even multiplicity, so the factor occurred an even number of times, the graph just touched the x-intercept and did not cross, turned it back around. The x-axis, where if our factor was a odd multiplicity, this is that factor occurred an odd number of times, then the graph crossed the x-axis at this intercept. So we're looking for our x-intercepts. We can tell what's going on with the graph, if it was going to cross or touch, depending on the multiplicities. We're going to find the vertical asymptotes, if they exist. We talked about doing that by factoring our denominator. And we factored also our numerator. And then we asked ourselves, is that factor of the denominator the same as one in the numerator? If not, then we have a vertical asymptote. Where that factor equals 0. If there was a common factor, then we needed to know, was that a removable discontinuity there, or was it a vertical asymptote? And so if they had a factor in common, we want to determine, is it a removable discontinuity? All the common factors. Cancel. If it did not, so if we factored and there was a remaining common factor, in the denominator after we simplified, then it's a vertical asymptote. So we found a vertical asymptote. We determined if there were any removable discontinuities. Then we want to determine if there is a horizontal asymptote, so looking at the degree of the numerator and denominator, or if there was a slant or oblique asymptote. So we just talked about doing that. We're going to compare both the degrees of our numerator and denominator to determine if it's a horizontal or slant/oblique asymptote. And then once we figured out where our asymptotes were, we're ready to start graphing. And the best thing to do is start to graph your asymptotes on your graph by denoting them with a dotted line. Plot any x and y intercepts that you found. And then we're going to have to probably plot a couple additional points. And the points that we want to choose a couple of points plotted on each side of a vertical asymptote so we can see what's happening to the graph around our vertical asymptote. Okay, so let's now look at an example putting this all together and graphing some rational functions. Okay, so let's say that we have r of x. R of x is a rational function. Our numerator of r of x, let's say, is x squared plus x minus 12. And then our denominator is x squared minus 4. So we want to go through here and we want to graph. So I would actually probably start by factoring our numerator and denominator. So let's rewrite r of x. I noticed that x squared plus x minus 12 factors. There are two numbers that multiply to give us our constant negative 12 and some to give us our middle coefficient of 1. and that would be +4 and -3. So x plus 4 times x minus 3 is how x squared plus x minus 12 factors, all over x squared minus 4, a difference of 2 squares. That factors as x minus 2, x plus 2. So looking at this, I was going to find my intercepts. We know that this occurs when our x value is 0. So we're going to go in here, and wherever we see an x in our function, we're going to plug in 0 for x. So we can go back in and we can plug this into our original function, or we can plug it into our factored function. If we go back in and we plug it into our original function, we have 0 squared plus 0 minus 12, all over 0 squared minus 4. So simplifying, in my numerator, I'm left with -12. In my denominator, I'm left with -4. -12 divided by -4 is +3. So we have a y-intercept at the point 0, 3. To find our x-intercept, they exist. We're letting r of x equal 0. We're setting our y value of our function equal to 0, and we're solving for x. I'm going to put it as my factored form of r of x. So again, I said that we don't have to look at the numerator. I mean, we only need to look at the numerator. We don't have to look at the denominator, because that, if we were solving this equation, we would clear our fractions by multiplying through by our LCD. Our LCD is x minus 2, x plus 2. So multiplying 0 times x plus 2, x minus 2, we still get back 0, is equal to multiplying this on the other side. The whole point was so our denominator would go away, leaving us with just the numerator x plus 4, x minus 3. It's factored already, so set each factor equal to 0. I'm looking when is x plus 4 equals 0, when is x minus 3 equal to 0. Subtracting 4 on both sides, x plus 4 is 0 at -4. And adding 3 on both sides, we get x minus 3 equals 0 and x is 3. These are factors which set, okay, yeah, the numerator equal to 0. So our x-intercepts, if I wrote them as points, are -4, 0, and 3, 0. So notice that each factor only occurred once. So our multiplicity that this occurred is odd. So we know that it's going to cross the x-axis at these values. We want to find any asymptotes. So let's find our vertical asymptotes. If they exist. Well, we already factored both the numerator and denominator. Looking at it, we didn't have any common factors of the numerator denominator. So we're looking at what sets our denominator equals 0, and those are our vertical asymptotes. So x minus 2 is equal to 0 at x equals 2. So we have a vertical asymptote at x equals 2. And we have a vertical asymptote when x minus 2 is equal to 0, or x plus 2 is equal to 0, which is when x is -2. So we have two vertical asymptotes. Let's look at if there is a horizontal asymptote or if we have an oblique asymptote. So this all had to do with the degree of the numerator denominator and comparing them. If I look at the degree of my numerator, my highest power is a 2, so that degree is 2. The degree of my denominator, the highest exponent in my denominator is also 2. So my degrees equal. So if the degrees equal, you have a horizontal asymptote. And it's looking at y equals the leading coefficient, so the number in front of the variable to the highest power in the numerator, which is 1, divided by the power of the leading coefficient in the denominator, which is also 1. So 1 divided by 1 is 1. So we have a horizontal asymptote at y equals 1. So let's go in now and start graphing this. Okay, so denoting our asymptotes, we had one at -2, x equals -2. So denote it by a dotted line. We had one at x equals +2. So a vertical line at x equals 2. And we had a horizontal asymptote at y equals 1. So denote it by a dotted horizontal line at y equals 1. We found our intercepts. We found an intercept at x equals -4. And we also found an x-intercept at -2. Right? No, x equals -4 and x equals 3. I'm going to say if it was -2, that's a vertical asymptote, so it wouldn't exist. But we're okay. And then we had a y-intercept at 0, 3. Okay, so knowing where my asymptotes are, I kind of understand what my graph is going to look like. But let's look at it together. And so you should always kind of see at least a couple points on each side of a vertical asymptote. And so I have one point on the left of x equals -2. I have this x equals -4. I know that it's crossing here. My guess is that it's going to cross like this and start hugging my asymptotes. But I can know for sure by plotting a point. So let's maybe plug in x equals -3. So let's make a table here. So when x is -3, I want to figure out what my y value is. I can plug it back into my original function, r of x, or I can plug it back into my factored form. Factored form might be a little faster and easier, but you can do whatever you prefer to do. So if I plug in -3, so r of -3, I get, for my first factor, I have -3 plus 1, which is going to leave me with a 1. And then I have -3 minus 3, so that would be -6. So 1 times -6 in the numerator, all over, plugging it in -3 into x minus 2. Well, -3 minus 2 is -5. So -5 all times -3 plus 2, which gives me -1. So 1 times -6 is -6, all over -5 times -1 is +5. So I have a point here at -3, -6/5. Okay, so I kind of really just wanted to know, was my point going to be falling above or the x-axis? And falling below the x-axis at x equals -3. It's about it's -1 and 1/5, or -1.2. Let's say that this is -1. I just estimate I have a point right here. So knowing this, and knowing that as x is getting closer and closer to -2, I'm going to be going to -infinity. I'm going to hug that vertical asymptote there. And then as x is going to -infinity, I'm going to be hugging my horizontal asymptote of y equals 1. So I have a graph that looks like this on the left of x equals -2. So notice I don't have any x-intercepts between my two vertical asymptotes at x equals -2 and x equals 2. But I do have this point here at 0, 3. I have a y-intercept. So knowing where my asymptotes are, I know I'm going to have this is going to somehow be hugging x equals -2 on the right-hand side, and it's going to be shooting off to positive infinity. And I'm also going to be, as x is approaching +2 on the left-hand side, I'm also going to be shooting off to positive infinity. So without calculus or graphing utility, I don't know, this could be dipping a little bit below at x equals 3. It might not be a vertex type of thing right here. And I wouldn't know that until I had some more tools. In this case, I would need calculus or a graphing utility. I could, if I guess I plug in a couple more points and see what's going on. So maybe I could plug in x equals -1. So if I look at r of -1, I would have -1 plus 4. So that would give me 3. All times -1 minus 3, which is -4. All divided by -1 minus 2 is -3. And -1 plus 2 is 1. So 3 times -4 is -12. All divided by -3 gives me back +4. So when x is 1, y is 4. I could do the exact same thing then, plugging in +1. So I would have 1 plus 4, so r of 1. 1 plus 4 is 5. 1 minus 3 is -2. All over 1 minus 2 is -1. 1 plus 2 is 3. Just plugging it back in for x where my factored form. So this is -10 divided by -3, which is +10/3, which is approximately 3.3. And then seeing what's happening to my graph on values bigger than x equals 2. I have 1 point, my x-intercept at 3, 0. Again, I can see what's going to happen just knowing where my vertical asymptotes are. But if you don't see it, plot 1 more point. So maybe x equals 4. So if we plug in 4 back into our function r of x, wherever we see an x, we get 4 plus 4, which is 8 for our first factor. 4 minus 3 is 1 for our second factor in the numerator. 4 minus 2 is 2 for our first factor, and 4 plus 2 is 6. So this gives me back 8/12, which 4 goes into both of those, so 2/3. So 2/3, it's about 0.67. So that right here. So I know as x is going to infinity, I'm hugging my horizontal asymptote at y equals 1. But as I'm coming into x equals 2, on the right-hand side, this will be shooting down to negative infinity. So knowing where our asymptotes are, where our intercepts are, and plotting a couple extra points on each side of a vertical asymptote, you should be aware of what the graph looks like. So it looks like we have time probably to do one more and then stop for the day. So let me pull up one more question for you. So our next example, f of x is equal to x squared minus 2x minus 15 all over x squared plus 6x plus 9. So you should be able to graph this rational function. I probably on an exam would break it down for you and ask you different pieces, like find your intercepts. So I know I can find my y-intercept, that's the easier one, by going in and plugging in 0 wherever I see an x in my function f of x. So going in, putting in parentheses wherever I see an x, so I have parentheses squared minus 2 parentheses minus 15 all over see an x, so parentheses squared plus 6 see an x, so parentheses plus 9. Put in 0 wherever you wrote your parentheses and simplify. Well, 0 squared minus 2 times 0, that's 0, minus 15 is negative 15. All over 0 squared plus 6 times 0 is 0, plus 9 is 9. I notice that 15 and 9 both have 3 in common, so I notice I can reduce this. 3 goes into negative 15, negative 5 times, and 3 goes into 9 3 times. So I have a y-intercept at the point 0, negative 5/3. My x-intercept, I'm going to set my equation equal to 0. So 0 is equal to x squared minus 2x minus 15 all over x squared plus 6x plus 9. I can clear my fraction by multiplying both sides by my common denominator, or LCD, of x squared plus 6x plus 9. Well, anything times 0 is always 0, is equal to, our denominator cancels with what we chose to multiply both sides of our equation by. So we're left with our numerator, x squared minus 2x minus 15. So 0 is equal to, I can factor this, or I can use the quadratic formula. And I notice that this is factorable. There are two numbers that multiply to a -15 and add to a -2, which would be a -5 and a +3. So that factors as x minus 5 times x plus 3. Now set each factor equal to 0. So x minus 5 is 0 when x is 5. And x plus 3 is 0 when x is -3. So we just found our x-intercepts. We have two of them. One is at 5, 0, and one is at -3, 0. Let's look at our vertical asymptotes. Let's factor both the numerator and denominator of our original function. So f of x, we just saw that the numerator factored as x minus 5, x plus 3. All over, and our denominator, I noticed that x squared plus 6x plus 9, that factors as x plus 3 times x plus 3. Well, notice we do have two common factors, x plus 3. Those cancel, and so what's left is where I'm going to have a vertical asymptote. I'm going to have a vertical asymptote, it looks like value which sets my denominator equals 0, is x equals -3 is what's left. Now looking to see about a horizontal asymptote or slant asymptote. Or oblique asymptote. That has to do with the degree of our numerator denominator. Again, looking at this, they're both the same. Degree in the numerator and denominator are both 2. And so I look at the leading coefficient of the numerator, which is 1 divided by the leading coefficient of the denominator, which was 1. So we have a horizontal asymptote at y equals 1. Putting our information together and graphing it. So graphing our asymptotes, we had one at -3, a vertical asymptote at x equals -3. So draw a vertical dotted line there. We had a horizontal asymptote at y equals 1. So draw a dotted horizontal line at y equals 1. We had an x-intercept at -3. Okay, so notice that this is not defined. We go back up here, our domain, x cannot be -3. So x equals -3 is not an x-intercept. And so we actually only have one x-intercept. Which is at +5. And then we had a y-intercept at -5/3. So that is -1 2/3, which is about -1.7. So we have a point about here. So I have 2 points on the right-hand side of x equals -3. And so I know what my graph is going to look like on the right of x equals -3. So this is going to be increasing. It's going to cross the x-axis at 5 because we have a odd multiplicity of that x-intercept. And as I get closer and closer to x equals -3, this is going to be shooting down to -infinity. And I know that because I don't have another x-intercept that it would turn back around and cross the x-axis. So it would have to look like that. Knowing I don't have any x-intercepts to the left of -3, my guess is that my graph is going to look like this for that piece. But I can show that by just plotting 1 or 2 points on the left of -3. So if I plugged in x equals -4. So if we go back into our original function and let's look at f of -4. If we plugged it into our factored form, I would have -4 minus 5, which is -9, divided by -4 plus 3, which is -1, which is equal to +9. So when x is -4, my y value is +9. Be up here. So this is going to get closer and closer to my vertical asymptote of x equals -3. It never crosses a vertical asymptote. It is possible it will cross this horizontal. If it does cross a horizontal, it's going to hug it on the other side when it crosses it. If you're curious of if it crossed, where it would cross, you're going to set your function equal to your horizontal asymptote. And so you would set f of x equal to 1 and solve for x there. We're out of time, so I'm not going to do that now, but we could look at another example on the next class period if you'd like.